Hello, everyone, and welcome to the webinar. We will begin in a few moments. If you have not done so already, please take a moment to respond to the poll on your screen. How many individuals are attending this webinar at your location? If there are more than 5 attendees present, please type the number in the questions box. We will begin shortly. Hello, everyone, and welcome to EPA's 17th Annual Drinking Water Workshop. We are glad that you could virtually join us today for Session 2B on Source and Treatment. Now we will hear from Tom Speth, who will introduce our first speaker and help moderate the webinar.
Great. Can you hear me?
Yes.
Excellent. Thank you very much and welcome. We're a couple minutes late, but we're pretty much on time. So welcome to Session 2B, Source and Treatment 1, and specifically per and polyfluoroalkyl substances, or PFAS. So a couple of quick things before we jump right into the speakers. We're going to have 3 speakers. We're going to go from one to the other, and we might not end exactly on the half an hour, but we should finish in an hour and a half, and then we'll have a half an hour for questions for all 3 speakers. So we'll throw up all 3 speakers up on the panel. And so while the first speaker, second speaker, and third speaker are all speaking, if you have a question for them, please type it in the chat box, or the question, the question box, not the chat box, the question box. Put in your questions in the question box, and then we'll organize those questions and then report out on them after the third speaker. So we're not going to do any questions until after the third speaker has spoken. So technical issues, there's a link down toward the bottom of the slide that you can contact Cadmus if you're having technical issues. Also, if you're looking for attendance certificates, we'll get those out for this session, but please be patient with us because we've got a whole week of talks to give, and we'll probably have to, at the end of the workshop, get back together and start sorting all that out. So it might take a little while to get those certificates out to you. So that being said, if you can find the slides in the handout section on this dialogue section on this dialog box. You can find the slides if you're interested in them. Also, you can find the bios and other things, and so you can use that dialog box to access some information. So with that, I'm going to jump right into our first speaker so we can get going on this topic. Susan Glassmeyer is our first speaker. She's a research chemist at the EPA's Office of Research and Development for the Center for Environmental Solutions and Emergency Response. Dr. Glassmeyer earned a Bachelor of Science in Chemistry from Xavier University and a Master's and Doctor degrees from the University of Illinois. Her research is focused on contaminants of emerging concern, both chemical, such as pharmaceuticals, and microorganisms in the water cycle. She has coordinated several projects examining the occurrence, state, and transport of chemicals of emerging concern in wastewater, surface water, groundwater, and drinking water. And with that, I will pass the podium on to Susan.
I'm just waiting for the share. Oh, here it goes.
Excellent.
Okay. So good afternoon, everyone. Today I'm going to be talking about a few studies I'm working on looking at PFAS and other contaminants of emerging concern in source and treated drinking water. Let's see. I don't know if I can just click this off. Okay. So just a quick disclaimer. Basically, everything I'm saying here is my personal opinion, not those of the government, either the US EPA or the USGS. So what I hope to leave you with today are some just basic understanding of these two studies. The first is looking at PFAS and other CCs in drinking water. I'm going to focus on the PFAS data, look at the chemical concentration trends, some of the occurrence patterns, where I think maybe the source of these come from, looking at some modeling work, and the role of granular activated carbon during removal. And then I'll turn to the second study where we looked at de facto reuse more in detail, going from a wastewater treatment plant down to a drinking water plant. And we're going to look again at some of the concentration trends and the source characterization, and talk about how the interdisciplinary work we're doing there really helps to give us a better understanding of what is going on in the environment. So for the drinking water project, this was phase 2 of a 2-phase project where we sampled the source water and the treated drinking water from 25 different plants from across the US. The map here on the right shows the number of locations in each of the US EPA regions. We kept the sites anonymous just because sampling for contaminants of emerging concern, unregulated contaminants in drinking water can be, I don't want to say risky, but it can be, putting information out there that the drinking water plants, they don't know what's in there. So we decided to keep the plants anonymous just to give them a little more safety and security to do the sampling. So in this project, we looked for 247 different chemical and microbial analytes, as well as doing a bioassay for estrogens. So as I said today, we're going to focus on the PFAS, but all the data from this project has been published so far. The overview paper in Stoughton, as well as the PFAS paper, were both published open access, so anyone can get a copy of that, no problem. Everything else, I'm a co-author on everything, so if you look up my name, you can find the papers, and if you really, really want a copy, shoot me an email and we can get a copy to you. For the method, this is not method 235 or 237 or 237.1. This is one that was developed in the US EPA in Office of Pesticide Pollution, OPPTS, by Scott Boone. Basically, it's a 250 ml sample that he extracted using an Oasis wax cartridge. That's the primary difference between it and 537. He used LCMS to analyze it, and he had really pretty low reporting levels. Every analyte was less than 1 nanogram per liter. And that's going to play into how the frequency of contaminants that we saw. So looking first at concentrations, just to orient you to this graph, the green bars are all the source water. The blue bars are the treated drinking water. The upper and lower whiskers are the 95th and 5th percentiles. The belts are the medians. And if you want to notice, there's a log scale for the concentration. So you can see there's quite a variety within each contaminant in terms of concentration seen both in the source water and in the treated drinking water. When we did the Wilcoxon paired sample test, only PFAS, the 7th acid, the PF-HEPA, and the 6th chain acid, PF-hexS, and PF-MDA showed statistically significant differences between the source water and the treated drinking water. Everything else was statistically the same, both in the source water and treated drinking water, showing that across these 25 plants, there really wasn't much removal during treatment. So we just happened to have of these 25 samples, 3 that were on large river A and 3 that were on the second large river that we called large river B. The 3 that were on large river A all showed a higher percentage of PFOA in their samples compared to some of the other congeners, whereas those on large river B all had a large PFBA concentration or contribution relative to the other ones. And at the bottom, I just gave 3 other locations, utility 4, which had the most contaminants overall, utility 22, which had the highest concentration of PFAS, and utility 24, which is a groundwater location, just to kind of show how different the different concentrations and different contributions were at these other locations, making the similarities between those on large river A and large river B even more pronounced. Large river A, these are collected over It was probably a couple hundred river miles and over a period of 6 months. Large river B is probably 1,000 river miles. And again, probably 6 to 9 months between sampling. So you can see these are persistent patterns within these different water systems. So we wanted to look at this a little bit more, and to do this, we applied the drinks model. If you're not familiar with this is a model developed by Paul Westerhoff and his group. Basically, they took GIS plottings of drinking water intakes as well as wastewater treatment plant outfalls. They used the volume of wastewater that's produced, and we're able to come up with this model of de facto reuse across the U.S. You can see, especially down in the southeast, there's several different places where 10, 15%, or even greater than 15% wastewater is in these source waters. So for contaminants emerging concern, which we believe a lot of it comes from wastewater, these are types of areas that would be very interesting to look at. But then we applied it to our data from this project. And I know this slide has a lot of going on, so let me try to step through it a little bit more. On this top left, we have the organic contaminants of emerging concern, so all the organics. These are the concentrations summed across them, and then we compared the sum concentration, plotted that against the percent de facto reuse based on the model. We had one outlier, utility 1, that had a higher de facto reuse, but we had some issues during sampling that we had to throw out a lot of samples. So if we exclude utility 1 and just plot the rest of it, we get an R-squared of about 0.3, which means 30% of the difference between the samples can be attributed to or explained by the de facto reuse. So that's okay, but then when we just look at the pharmaceuticals and what we call the anthropogenic waste indicators, so things like surfactants and cholesterol and some other things we have in these methods that aren't PFAS. So we just look at those and again exclude 0.1. Our R-squared increases to about 0.52. So 50% of the difference between the samples can be explained by the de facto reuse percentage, which for environmental work is pretty darn good, I think. So that's interesting. It shows that most of these compounds probably do have a wastewater source, and that's a strong indicator of what's going on there. Now, if we compare that to PFAS, even if we throw out utility 1 and if we throw out utility 2 or 22, which had very high concentrations, at best we're going to look at 0.15%. So 15% of the difference in the concentrations can be attributed to DFR. So this really kind of suggests that PFAS isn't coming from wastewater in these locations. There could be other land-based sources. It could be atmospheric. We don't know. We didn't design this project to specifically look for what was causing these in the source water. But it just kind of gave an interesting trend to look at more. And I want you to kind of put a safety pin in this, and we'll think about this more in a couple minutes when I talk about the other project. So when we look at treatment, again, to orient you to the graph, on the top, again, the green bars are the source water, blue bars are the treated drinking water. And on the top, we have the number of PFAS that were qualitatively detected in each location. And you can see every location, regardless of the size, had at least 4 PFASs detected within the samples. On the bottom is the concentrations. Again, green bar source water, blue bar treated drinking water. And you can really see this is a log scale again. So even though the number of PFAS detected were pretty consistent at between 10 and 12 for most locations, the concentrations were very variable. From utility 5, which was a groundwater location having only trace amounts, to utility 22, which had quite a bit in there, both source water and treated drinking water. We'll be look to see, what might be causing differences or what removal can we think about. We focused in on GAC, granular activated carbon. That's known in the literature to be one of the main drivers of removal in these different treatment plants. So the plants that use granular activated carbon on the top and have their depth of their beds on the top, and on the bottom is the recharge rate that they do. that they told us about. So this bottom line, looking at the Wilcoxon P, only 4 utilities showed statistically significant difference between the source water and the treated drinking water. Those are utilities 2, 3, 18, and 25. And all those, utility 2 particularly had very deep beds and very short recharge rates. So their granular active carbon was fresh most of the time, allowing for better removal of PFAS. So for the take-home messages from this part of the story, we had the 25 paired source and treated water samples. All 50 samples had detectable PFAS in them. 1 treated drinking water, the utility 22, exceeded the health advisory guidelines of 70 nanograms per liter for PFAS and PFOA summed. We saw those distinctive PFAS patterns on the 2 large river systems, one that was dominated by PFOA, the other dominated by PFBS. And it looks like that PFAS is not strongly linked to de facto reuse percentage, so perhaps a non-wastewater source for those, but again, we don't have enough data to really be definitive on that in the study. And we also saw minimal removal during drinking water treatment, but the granular active carbon depth and recharge rate really do play a role in the removal, at least in this study. So from the study, we had some lessons that we learned that we wanted to apply to the second study to better assess how the fate of transport of PFAS and other CECs and what we could find out there. So, you know, for the most part, when we do occurrence studies, we're looking at targeted grab samples. And that gives us a snapshot of the concentration, but that's pretty much all it gives us. It only gives us, you know, a snapshot of the things we're looking for. We can apply other things like integrative samplers that deploy for 30 days or more. Those can give an idea of things that either are, you know, right below our detection level. By having these integrated samplers, we can get a sample above the detection level and see some of those compounds, as well as things that might be only intermittent and just weren't happen to be released during the time we're sampling, so we can get an idea of some of those things. Additionally, we can do non-targeted analysis, and this has really been a trend now that we can get more detail for a large number of chemicals. You know, there are some of these samples you can get 3,000, 4,000 different features, you know, different chemicals that you can eventually try to figure out what they are exactly. As well as the bioassays. You know, bioassays give you the effects, and it gives the effects of mixtures. So that way we may not know the individual compounds that are having an effect, but we can look at them together and see, you know, what their combined effect is. And that's actually more applicable to environmental studies, because, you know, a fish doesn't only get exposed to one thing, they get exposed to a gamut of compounds. So by having the bioassays, you can better understand that. So for this project, we had 6 samples that we collected along a river system to look at the fate and transport of CC. So we went upstream of a wastewater treatment plant. We had at the effluent pipe, what we call the effluent mixing zone, where the water was well mixed with the river system and the effluent. Point a little further downstream, the drinking water intake and the treated drinking water. So we sampled this one stream reach 3 times in October 2014, April 2015, and August 2015 to try to get some seasonality out of the samples. We had, in addition to these 6 sampling points, at 4 of the points, we deployed passive samplers, the POSIS devices. We had those in the upstream sample, the effluent mixing zone, the drinking water intake, and the treated drinking water. So the wastewater treatment plant was a little smaller than we had hoped. It only was 1.2 million gallons per day production. And it was a little different that they used UV disinfection for the primary disinfectant instead of chlorine or chloramine. For the drinking water plant, it had a 4.5 million gallon per day production. It used a combination of ozone and chloramination as a disinfectant. I also used a GAC. They were in the previous study, and they were one of the locations that had removal shown using the granular activated carbon. So our sample collection was with this extremely high-tech device. Basically, it was 2 4-liter bottles that we corked and then submerged about 2 feet below the surface of the water, pulled the cork out and got the samples there. We then decanted the water into the various sample bottles for the project. For the effluent, you can see this is the pipe coming right out here from the wastewater treatment plant. So we're able to stick the bottle right in the pipe and get the sample that way. At the drinking water treatment plant, they had sampling taps both for the source water and the treated drinking water, so that made it very, very easy. And then only one method used field filtration. Everything else was a whole water sample sent to the laboratory. So for the assays, we did a wide variety of assays. In total, we had 236 different compounds, but there were some that were in multiple methods. Some of the caffeine, carbamazepine, some of the other pharmaceuticals were in multiple methods. So we can look at, again, at different method performance, but we're going to focus on the 236 unique analytes for the rest of this discussion. So when we want to look at the frequency detections, just to orient you to this graph, the blue bar now is round 1, the green bar is round 2, the gray bar is round 3. So this is October, April, and August. And then we have the upstream, the effluent mixing zone, downstream, drinking water intake, and treated drinking water. And we had some issues both with transport and sampling. So the y-axis is not the number of samples, it's the percentage of the analytes with detections based on a given round. So for the second round, we only had 203 different compounds. But you can see an expected trend. You know, we have an increase in the number of compounds in the effluent samples, and then as we go downstream, has a decrease, and then from treatment, you get a further decrease. So, you know, that was good to see what you expect. In terms of concentration, we had to separate these for the organic chemicals on the top and the inorganic on the bottom. You may notice the kind of a difference here with the effluent samples. You know, most of the time, round 1 and round 3, the flow of the river was lower, so the concentrations were higher. But in the effluent, you can note the bars looks like it's kind of missing here. Basically, what happened was sucralose. We had a the matching LFM, the matrix spike, showed greater than 100%, 50% recovery. So we had to flag that as a qualitative analysis. But pretty much the missing part of this bar of about 20,000 nanograms per liter was just sucralose, so just artificial sweetener. So I thought that was kind of interesting. But you can see, you know, with the organic chemicals, a much steeper increase in terms of concentration from the upstream to the effluent, and then a decrease with dilution as you go downstream. Whereas the inorganic chemicals, it is still a slight increase, but the concentration is a little more stable between the samples, and that's partially due to the source of the compounds. So if we look at some of the individual analytes that had high frequency detections, these are just the organics. You see, you know, definitely the spike in the effluent for most of these compounds, you know, big spikes, and then decreases as you go downstream. And in some cases, you know, they're not even present in the treated drinking water or the drinking water intake. And some of the inorganics also showed the same trend, where we had the increase in the wastewater sample, the effluent sample, and then decrease as you go downstream. And with the fluoride, you can even see the addition in the treated drinking water sample based on the fluoride addition for dental protection. But most of the, or many of the inorganics, there really wasn't a significant trend, or you couldn't see a spike in at the wastewater effluent. And in some cases, like with barium here, you saw a decrease, which I'm not sure. I think maybe just, you know, dilution from the effluent coming out. Maybe we have to still think about that a little bit more. But definitely no significant increase at the drinking water treatment plant, or the wastewater treatment plant effluent for these compounds. And then we look at PFAS, you know, it's the same story as most of the inorganics. There really isn't a high spike in the effluent samples for any of these compounds, which indicates, at least in this river system, PFAS most likely is not coming from the wastewater, or it's not the most significant place where these compounds are coming from. What that source is, we cannot say, but it's most likely not the wastewater in this case. So, with those grab samples, we know everything there is to know about the system, right? You can probably guess my answer is wrong. So this is just an example of the POSIS devices, the Polar Organic Chemical Integrative Samplers for the pharmaceutical method. So on the left are the number of compounds that we saw in the grab sample compared on the right to the number of compounds that we saw in the POSIS extract. And you can see, there's in some cases nearly double what we see in the POSIS than we saw in the grab samples. So there are, things that are present in the water system that the grab sample, either due to the concentration or to the time that we collected it, we were not able to see in the sample. So, definitely having the POSIS gives us a better understanding of what's going on. So that's all we need, right? Again, you can probably guess my answer is no. The bioassays really give a great understanding of what's going on, or a better understanding. And this is a paper that came out earlier this year, where compared to some of the different bioassays, and for the estrogen bioassay, we compared the bioassay results to those of the analytical chemistry results, the LCMS-MS, and we got an R-square of 0.89. So, really good correlation. So pretty much the hormones, the endocrine compounds that we're measuring by the LCMS might be is providing the significant amount of we're seeing in the bioassay. So the effects in the system are caused by the things that we're already measuring. Now compare this to the glucocorticoid results. We saw pretty significant hits in the effluent samples. So there's a glucocorticoid response, but we didn't have any compounds, or we only had 4 in our methods, and we had no detections. So there's something there in the samples that are causing the response, but we cannot explain what it is. So this is an example of, where the targeted chemical listing is not meeting what we need, and we need to do more work here to figure out what that is. For another assay, we did a metabolomics analysis, and with this, there was 2 different extracts. One was the hydrophilic compounds, and one was the lipophilic compounds. And the hydrophilic compounds showed, a very significant, or it showed the same pattern that we saw before, an increase in the effluent and then decreasing as we go downstream. Whereas the lipophilic compounds showed the increase in the effluent, started to decrease, but then we saw an increase between the downstream sample and the drinking water intake. That's not really explained by the compounds that we saw, or that we measured in the with target analysis. So there's some contaminant being put in between the two. There are no tributaries. That's one of the reasons why we chose this river system. But there is a large bridge crossing the water system between the downstream sample and the drinking water intake. So maybe there's some runoff from that, or there are a couple industries with NPDES permits in the area. So maybe that's what it is. We still need to work on what the cause is. But it just shows that how doing this metabolomics analysis, we find out more about the water system than we would have had with just the grab samples. And again, this paper has been published already if you want to look more into detail on this. So with the non-target analysis, this is still forthcoming. This is really an evolving field, and we wanted to make sure that we did things the best way. So we had a lot of discussion about different standards and stuff to add in, so that way we can compare apples to oranges with all the different tests that we're doing. But we're hoping that some of these non-target analysis can look for specific chemicals, specifically some of the glucocorticoids, that might be able to explain what we're seeing in the bioassays. And it may identify other chemicals that either have wastewater or land-based sources that are not in our target list. For example, there are many other sweeteners, artificial sweeteners that we didn't have on our list, so maybe they can look for some of those. So in conclusion, the factor water reuse can result in wastewater-derived chemicals coming into both drinking water source waters and also into the treated drinking water. By doing a companion of the targeted chemical analysis, non-targeted chemical analysis, and the bioassays. Each one provides an incomplete analysis, but by combining them together, we get a better understanding of what's going on. And sampling protocol to look at things in different ways can really help give insights in these complex chemical mixtures that are coming from wastewater treatment plants and going into drinking water treatment plants. So with this, I'd like to acknowledge my co-PIs, particularly Scott Boone, who did the analysis of the PFAS samples for this project, for the drinking water project. And then also the team for the de facto reuse. That was a large group of folks across the US, in particular Ed, Dana, and Mark, who are my co-PIs on that project. And I'd like to thank you for your attention.
Okay, great. Thank you very much. Oops, sorry. Thank you very much, Susan, for that presentation. Pretty much right on time. So thank you with that. So we're gonna jump right to our next talk. And our next talk is David Dani, is the Emerging Contaminants Coordinator for the Colorado Department of Public Health and the Environment. Previously, he oversaw training for Colorado's Safe Drinking Water Program and provided leadership for the program's acute team that works with drinking water providers during emergencies. He was the lab manager at CU's Drinking Water Optimization Lab and project lead in Peru and Nepal with Engineers Without Borders. And with that, I'll hand it over to David. But one just reminder to the audience that we will be answering all questions at the end of the third talk. So if you have any questions for Susan or David or Scott to follow, please type them in the question box, and then we'll have a panel discussion at the end. Thanks so much. And David, the podium's all yours.
Hey, thank you all for inviting me to speak at this. Excited just kind of what we're doing in Colorado and some of the steps we're taking to address PFAS. And one of those steps was a large statewide sampling project. And so there were some interesting kind of findings for us from the sampling that I'm happy to share with you today. So kind of what I'll be covering over just the next half hour is a look at just what we're doing in our state. We have a PFAS action plan, kind of similar to what EPA has to address PFAS. And then, in kind of step with that plan, we did a massive statewide drinking water sampling project. So I'll be sharing just the results of that project, the key findings, and some of the takeaways from that, and then what we're doing with that information and next steps taken. So our state's PFAS action plan is really just breaking the chain of exposure. So on the right is the graphic that, PFAS ends up in the products that we use and where those products, and that end up going to landfills, water treatment plants, ultimately get passed along to the environment, and where the PFAS is used in the firefighting foams. And so, from there we see it kind of enter into our waterways and drinking water and some of the food we eat. So our PFAS action plan is really just trying to eliminate or minimize those exposures, expose us to PFAS. And our top priority is just to find where do we have impacted drinking water in the state. And so we did this massive study to get an idea of, which drinking water is impacted. If you will, just where we have sites throughout Colorado, and where we see anything above the EPA health advisory that we're trying to use to reduce exposure. And then also we kind of track all the PFAS levels and where they are throughout the state through time. The rate that these levels are just going to keep getting lower and lower. And we're seeing this just with some of the other states that have gone in and set their own drinking water standards. And And also, we're using regulatory authority to help kind of reduce exposure and minimize just new contamination. And then proper PFAS disposal. So in remediation and in addressing that, just making sure PFAS is disposed of properly. And then in our state, there was a bill. So every 3 years, we do a fire district survey of, it's voluntary for all the fire districts statewide, but who's using PFAS, how much do they have on hand? And part of that bill also bans the use of PFAS in testing. And then we're just staying engaged at the national level, just seeing what everyone else at EPA, the USGS, and other states are doing so we can learn as much as possible. So before jumping into the drinking water project, a couple other things just wanted to highlight that might be of interest to other states that's new is we had 2 bills that recently passed. One is House Bill 2011-19. And what's interesting in that bill is it creates a certificate of registration program. So essentially any entity in the state that's storing or using PFAS foams will have to kind of register, which is great. So essentially we'll be able to know where is PFAS throughout our state. And that kind of helps with that inventory that we were talking about. And it also creates kind of a standard that everyone needs to follow for capture and disposal of PFAS. So we're going through stakeholder processes, kind of creating those aspects. And then there's entities that do have to test foam, so it cleans that up for those entities that do have to, that are required federally to test their foam systems. And the other is State Bill 2218. And this really kind of starts creating a fee on the fuel products where you actually have to use PFAS foams to put out fires associated with those. So with these fees on the truckloads of the fuel products, it creates a fund that we can then use to help impacted communities. So we'll be able to go in and do additional sampling, health assessments in impacted communities. We're looking at putting together a take back and disposal program, similar to what other states have done. And then where we find communities and water systems impacted by PFAS, there's a fund to help them out. And the main goal with this is, a lot of times these foams are used to, save lives. And so what we don't want is another town suing another town or finding out that their volunteer fire departments, years ago, before understanding all the health impacts from these chemicals, to use them and now contaminated their own drinking water. Yes.
Yeah, David, this is Tom. Sorry for breaking in. We're getting a lot of notices that people can't see your slides, but I believe it's on the people's screen, so the attendees screen. So if the attendees could refresh their screen, and I've been told you can refresh your screen by exiting the full screen mode, and that may help with the situation. Sorry for breaking.
Oh, great. Yeah, do you want me to give a minute just to allow people to do that, or should I continue?
Yeah, it should be pretty quick. If you're still having problems as you exit and out of full screen, and chat back with us and let us know, and maybe Cadmus might have a second solution. But I think that should help. So I think you can keep going.
Great, thanks. Yeah, and all these slides will be presented later. So
yeah, in fact, David, these slides are in the handout section. So if somebody wants to go to the handout section and get the compendium slides, this slideshow is in there. So you could look at that as an alternative.
Tom, so in the past about PFAS in Colorado, and so from the unregulated contaminant monitoring rule for EPA, we found out there were two systems, Security and Wide Field, that were impacted by PFAS by an Air Force base. And at the time, we thought, well, maybe that's it. Those were the only two that had identified PFAS above, at the time, the health advisory level that we were using. And then after that, we had two volunteer fire districts that read about this and said, well, we use these foams. Let's test our own fire station's water. And sure enough, they came back with levels above the health advisory. So all of a sudden, it's kind of growing of, well, maybe this could be in a lot of different places in our state. And we also had a water provider that did test that came back non-detect when testing for EPA as part of the unregulated contaminant monitoring rule, that went in and tested individual sources. And they had some that came back pretty high above the health advisory that they've since shut down. That's what was eye-opening, is essentially we've had drinking water sources impacting around 100,000 people, and kind of highlighted with the stars there, and blood work that's been done in that Security and Wide Field area showed that folks through drinking water exposure had levels in their blood 2 to 12 times higher than the national average. So that's kind of why our main focus is on drinking water right now. But the rest of the state, we really knew nothing about. And so because of that, to get more information, we were given $500,000 from state legislature, emergency funding, essentially to look statewide and see where we have impacts to drinking water. And so communities can learn if their residents are at risk. And with this money, we offered free testing to all public water systems that are community or non-transient, non-community. So those are the ones serving schools and workplaces. And the testing was for systems that have their own sources, so not ones that are purchasing water from another entity. And we also opened it up to all the fire districts with wells that were interested in testing. So what was interesting was we don't have the authority to force testing. So this was a voluntary effort. So we had no idea how many people, and systems would actually sign up for this, just knowing the risks of, kind of what could happen if they find it above the EPA health advisory. The other interesting thing, we, in a questionnaire to all the systems, when we were kind of letting folks know about this free sampling to them, most entities chose to do their own sample collection. And there was a choice in there whether they wanted contractor support for sampling. So this was something we didn't know what they would decide. Actually, it worked out really well, because right after, we started doing sample collection, and that probably in about March, right as COVID-19 ramped up. And so this was, because there's emergency funding, we essentially had 6 months to complete the project and get results back. And we had to do it in the middle of kind of, COVID and a lot of restrictions going on. So it worked out well that everyone chose to do their own sample collection. We used EPA method 537.1 that measures 18 different PFAS compounds. Just due to cost, we didn't do field reagent blanks that are part of the method, where if you get a detect, you would then run the blank sample to essentially see was that contamination actually in the water, or possibly something from, the sample collection part of it. And also COVID-19 restrictions, we had to delay when we got all of our results back. And so, our plan was to actually get results back and then go back and resample locations with field reagent blanks where warranted. And we weren't able to do that since we had to push back getting the results. Part of this project, we put together a large frequently asked questions, public notice templates for water systems and fire districts, so they could share their results if they're above the health advisory, and also templates they can use to share their results that are below the health advisory. So we're encouraging everyone to share their results. And all of these resources, results, everything I'm sharing is on our website. And so I'll have a link at the end of this presentation. So feel free to go and use whatever you find and reach out with questions on that. And part of this, if there were results above the EPA health advisory, we'd coordinate with water systems to notify the public and work with them to reduce that exposure. So everyone going into it knew if they did have results above the EPA health advisory that they would be sharing those with their customers. So right away, just getting $500,000 in state funding to go look for PFAS, everyone came knocking on our door. You know, counties, we had media, public organizations, everyone asking, well, so this is voluntary. We want to know who's signing up and also who's not signing up. So we created a dashboard that's still available on our website. So it shows, you know, who's eligible to test, and then who's essentially how many have signed up. And we had, you know, about 50% of our community systems and everyone eligible, serving about 75%, 3/4 of our population. So we did have a lot of the larger systems sign up. And part of this, what you can do, you know, as a customer or just individual, you can go and click on, you know, the county, and then below it just shows here's all of the water systems, and you can see, did they actually sample for PFAS, yes or no? So this is all information that's there, so you can, you know, right away if your water provider did participate in the project. And we're very clear to say that this is only for this project, and there's other water systems that have proactively gone out and done their own sampling outside of this. And so this is a map now showing, you know, after we completed the sampling project, all of the sampling that was done. And so it just shows, you know, the good news for us was we really did get outside of just the big urban areas of Denver, Colorado Springs, and Grand Junction. And we did get a lot of, you know, entities and smaller water systems kind of out in our eastern plains and into the mountains and far corners of the state that were interested and signed up. So now just the results and key findings from this project. And so we did have 400 water systems that signed up. Luckily, we didn't have anyone serving treated drinking water above the EPA health advisory. So all the water systems that signed up were able to sample all of their entry points. So these are all the points of treated drinking water kind of entering their distribution system for consumption. And this was using the EPA health advisory of 70 parts per trillion for PFOA and PFAS combined. And we had 2 water systems that had source water, so this is untreated water above the EPA health advisory. And both of those systems were ones that had previously tested and we knew about from the unregulated contaminant monitoring rule. So we'd already worked with them. They put in treatment via on exchange. One stopped using those sources, but they took advantage of this program to get more information on levels in those waters. We had 15 fire districts that signed up to test their wells, and 2 fire districts with source water that came back above the health advisory. One was one of the fire districts in the hills above Boulder that we had already tested and wanted to test again. And one was a new one that we're working with now to identify if there's any impacts to private wells in the area. Luckily, there's not anything within a half mile of this fire station. So we're really not anticipating much impacts to private wells, but we're going out now and working with those folks to do some additional testing just to make sure. And 71 surface water sites. So additionally, we were able to go out and get information on our surface waters. One thing that was interesting is we had detects at all of the sites tested, which was surprising since we're a headwater state. So a lot of our surface waters coming off of snow melt and that. And then we had one result above the EPA health advisory in a pretty industrial area, just kind of north of Denver. And really, it's a drop in the bucket of what we're able to test. There's so many surface waters throughout the state that we would like to get more information on. So something we'd like to do in the future. And of the 18 PFAS compounds that we tested, PFAS, PFOA, PFHXS, PFBS, PFHXA, and PFHPA were the ones that all showed the highest actual concentrations of all the samples, and they were most prevalent with detections in greater than 20% of the samples. So this is kind of our kind of most wanted or hit list that we're really going to be kind of looking at, both concentrations and where they're showing up moving forward, and really seeing just kind of what health information is out there for these to see if it's something that we need to kind of go in and further address. And, one thing, we are using the EPA health advisory, but, there is a lot of information and stuff that we've put together explaining, well, why are you using EPA health advisory and why aren't you being as protective as, say, another state that's adding 5 or 6 of these PFAS and set a MCL limit at 20. And so, we're trying to get different toxicology resources and folks on our end to do a deeper dive into that. And then, in the meantime, just really looking at all the information nationally coming out on those 6 compounds in particular. And one thing that I found interesting, especially after reading in the news, that they were detecting Gen X and Adana, which are some of the replacement compounds for PFAS, PFOA that have been phased out, that they're seeing these replacements up in the Arctic in samples. And, of over 800 total samples in our state, we only saw 2 come back with detects for both Gen X and Adana, and those were at really low levels. So they seem to not be an issue here in Colorado. So this is kind of just some graphs showing a lot of what I just talked about. And in this graph right here is all of the treated drinking water. So there were 397 water systems that tested their treated drinking water. The blue bars show the combined PFAS and PFOA to compare against the EPA health advisory. And the red is the total PFAS of all 18 compounds added together. And we took the highest entry point sample from each system for this kind of graphical display. But kind of the big takeaways are, you can see for not detected, about 3/4 of the systems didn't detect PFAS or PFAS and PFOA. And for detection, we use the actual method detection level and not the reporting level that a lot of other states are using. And so you can see if we use the actual reporting level, the less than 1 part per trillion, even some of the 1 part per trillion to 5 parts per trillion would also probably get lumped into not detected. But we decided to use anything the lab identified as detected, we would show with an actual value. So we have one system with treated water above 70 parts per trillion. It was just one of their few entry points. They indicated that they know that it's impacted by a nearby fire district, and so that's kind of another site that is impacted with the PFAS foams. And I mean, the great news, we only wondering how many we'd actually see for above the EPA health advisory. for PFAS and PFOA, our highest levels were between 20 and 30 parts per trillion for those two compounds. And then looking at drinking water sources, like I'd mentioned, essentially, for total PFAS, there was only one groundwater source that came back not detected. So whether it's the modified 537 method or it's just really showing up in all the raw water is something that we need to kind of further look into. And then, lots of the concentrations are at lower levels, but there's a few that were at higher levels. The two for PFAS and PFOA that I'd talked about earlier that we'd already known about. And there were two additional systems of total PFAS above 70, and contacting them, they both use reverse osmosis just for other water quality issues. So, having that, their treated water looks a lot better for PFAS. Concentration, so this is just additional rivers and streams that we tested. All of them had detections, and we looked at some that go through different urban areas, and those were the ones that show up above 70 parts per trillion. So you can see that, in our state, we did show wastewater and different contributions that do make an impact in our waterways for PFAS. So next steps, we are following up with all the water systems that had higher levels in both our treated and source water. And then we're overlaying where did we see higher levels of PFAS. And then with that, working with EPA is all of the potential or known PFAS sources. So these are all the airports, all 300 fire departments, ski resorts are listed, landfills. So overlaying all of that to see, okay, we had a higher result in, this town. It's so far from this PFAS source that could be, kind of the cause of the PFAS. And looking in really, do we have, things that are closer to that PFAS source, private wells or even other water systems and their sources that could be impacted and potentially be even above the EPA health advisory. So that's an analysis that we'll be doing in and then doing further sampling if needed to ensure that no one's getting water above the health advisory. We're using our hazardous waste authority to require various sites that are doing cleanup activities to evaluate for potential impacts to groundwater from PFAS. And then we have a policy that just passed where we can get more data on potential PFAS discharges to state waters. So, any discharge to a state water, if there's a potential for PFAS to be in that water, they'll be monitoring for PFAS, and the policy also provides guidelines to be able to go in and, depending on the levels of the PFAS, to go in and set actual discharge permit limits. So it provides guidelines there. And with that, thank you for your last half hour of your time. There's a link right there, and these slides will be shared where you can get more information about the project, all the results, and my contact info. And it sounds like we'll be taking questions at the end. So thank you again, and back to you, Tom.
Okay, great. Thank you, David. And right on time. So perfect. So we're on time. We recognize that during David's talk, he had a little bit of audio visual problems, especially on the slide end of things. A number of people had problems, and we apologize for that. I've been told that refreshing your browser works for some people. Get the screens back, get the slides back. Exiting full screen works for others, and logging out also works for others. So it seemed to be kind of a mixed bag in terms of what solves the problem. So if this happens again, please try refreshing your browser or exiting full screen mode or logging out of the system and then logging back in may work. So, and again, I apologize if you had problems during David's talk. The slides, David's slides are in the handout section, and we'll be sending out the slides for all three speakers and for all the sessions later on. So let's get on to our third talk. We're right on time. So our third talk is from Scott Alderman. He has a Bachelor's of Science in Environmental Studies and Geosciences from Hobart and William Smith Colleges, and a PhD in Environmental Engineering from Rensselaer Polytechnic Institute. His graduate research focused on the use of organic peroxy acids to degrade persistent organic contaminants. He currently works for the New York State Department of Health Bureau of Water Supply Protection, where he is the chief of the Bureau's compliance section. And with that, I will hand the podium to Scott.
Okay, thanks, Tom. Let's see if I can get this up quick here. Okay, how's that? All right, again, thanks, Tom, and thanks, EPA.
Sorry, real quick. Yeah, could you swap the display real quick?
Okay, I knew I was going to mess that up.
Yep, no worries, all set.
Great, okay, thanks. So again, thanks to the EPA Office of Research and Development for inviting me to share this research objective, really this investigation that we did, the New York State Department of Health did on a medium-sized public water system impacted with PFAS contamination. What I intend to get done with this presentation is to first just quickly go through the properties of PFAS compounds and discuss some of the information that we came across with the treatment or the efficiency of treatment with granular activated carbon. We'll go into the research objectives for the reason why it was that we did this study, provide a system overview, very similar to Susan's presentation. I'm going to try to scrub any information that could identify the public water system. So I will go over an overview of the unit processes for the system, and then just discuss the observations and some of the data that we had and some conclusions. And so I won't spend too much time with this because I'm sure the folks that are listening to the presentation are very familiar with these compounds at this point. Two examples that I'm showing here, PFOA and PFAS, the octanoic acid 8 chain, and then the sulfonate 8 chain. I like to look at, and before I was with the compliance section of the health department, I worked in the design section, and so whenever it came to treatment of emerging contaminants or treatment of any kind, really, I like to start with the chemical structure to get a sense of how we think that compound will behave not only in the environment but in a treatment plant or a treatment system. And you can tell with these compounds, these chains, the long chains are a hydrophobic portion of the compound with the hydrophilic head, both for the carboxylic acid functional group compounds as well as sulfonate compounds, which makes them very effective as surfactants, and they were used extensively for emulsion polymerization in creating other compounds or other making other materials more efficient or effective at what they do. So I think in New York State anyway, we've seen the industrial use for use as emulsifiers prevalent, as well as the firefighting foams. We've seen that use, and we've seen contamination associated with those uses. The compounds, because of the carbon fluorine bond, are very stable in the environment, meaning that they have long half-lives in the environment, and not only long half-lives in the environment, but also long half-lives. Certain compounds have relatively long half-lives in the human body as well, which kind of drives the health advisory levels or the MCLs or discussions of MCLs. So I think really our story, or my story, the health department's story with these compounds came about with the detections that were coming out of the EPA's UCMR program. And so we started to see communities that were detecting these compounds, and we needed to, since the Bureau of Water Supply Protection houses the design section, whose responsibility it is to review modifications to existing treatment facilities or installation of new treatment facilities. We had this compound, we needed to learn what it was and what was the best available treatment technology. So our first thing was to go to resources available, both online and in the scientific literature. And what we were finding was that GAC was being identified as an effective treatment for PFAS compounds. But what we were also finding was that GAC wasn't necessarily treating all PFAS compounds equally. And to go back to the structure argument that I was just trying to make, the larger the compound, the less hydrophilic the compound will be, the more readily removed from a treatment process like GAC, as opposed to the shorter compounds. And so that's what we were seeing in the literature. GAC was preferably removing long-chain PFAS. Removal efficiencies for shorter compounds were lower. The use of efficiency, I'm a little bit careful with using the word efficiency when we talk about removal with GAC. It becomes a little bit difficult to have conversations with stakeholders when, for example, if you're trying to present that the removal efficiency for PFBA is, say, 80%. To a stakeholder, when you say 80%, and their immediate response is, okay, well, that's removing 80% of the compound, but you're still passing 20% of the compound on to me. And that's not necessarily the case. And that's not what we see with GAC. So the efficiency for the short chain compounds is lower than the long chain, but there are, either way, there are treatment circumstances where you can get non-detect for even the short compounds using granular activated carbon. We were also finding in the literature that if you had mixtures of PFAS compounds, you had to be mindful of the competitive sorption that's going on in the GAC system, whereby you may be driving short chain compounds that had the ability to initially absorb the GAC from it after the long chain compounds were coming. And also one of the things that we saw in the literature was a preference for the carboxylic, or a preference for the sulfonates to be taken up by granular activated carbon as opposed to the carboxylic functional group. And again, I think that has something to do with the solubility of the compounds, relative solubility of the compounds. So the objectives, or how the project kind of came about, we had a system that was impacted by a mixture of PFAS contamination in their source water. It was a medium-sized system. It was relatively close to where we were housed, where our offices are housed in Albany. We have very good laboratory capabilities at the Department of Health, had the ability to analyze for 16 different PFAS compounds. The mixture that we had for the impacted community was a mixture of both long and short chain compounds. It was a system that had been reviewed and approved by our bureau, and it was a lead lag system. The optional sampling ports that you can get on the GAC contactors, they were installed in this system. So we had the opportunity to look at different depths, take samples at different depths of the full-scale system. And we're really interested in taking a look at ground truthing the design projections as well as the literature. So it's a relatively new compound that we were working at providing treatment for. We had engineering studies that informed the full-scale design. So this, in a way, was an opportunity for us to take samples and see how well were the engineering projections and how consistent with the literature is the system that we're seeing. So what we did, and I'll give you a system overview first. So it was a medium-sized municipal water system. It was a GWIDI system. They had been determined GWIDI, I don't know, some 10 years before this event. And as a result of the GWIDI determination, they installed microfiltration. So the total capacity of the system, as shown here, and if I can figure out how to get my mouse to work for me here. Medium-sized system designed for 1 million gallons per day. And essentially, it's a well system, GWIDI system. It is impacted with iron, and so they do a pre-treatment with permanganate and chlorine, depending on the concentrations. That permanganate goes into a contact tank where they can remove the iron before it gets to the microfilters that they installed once they were determined GWIDI. And this would prevent the iron scaling on the microfilters. That water then gets chlorinated for disinfection, goes to a clear well before being sent to distribution. So what they were able to do once they were discovered to be impacted with the PFAS contamination was to shoehorn in GAC filters into between where the microfilters were and the clear well, so that they put their lead lag system after pre-treatment when they would get the best water quality. Essentially, they'd removed everything but the PFAS compound because none of the upfront unit processes was going to have any impact on PFAS. So what we were able to do, and like I said, the vessels that were there had the sample ports on the side. And I know we're showing 3 sample ports here on the side, but the vessels do have 4 sample ports. There is one additional port here that samples what's called the undercone area of the contactor. That undercone sample would be representative of what we could get at the midpoint. So this midpoint sampling location acted as that 4th sampling point. And so we were able to take samples at 9 different locations, the influent, each of these ports, the midpoint, which acted as the influent to the next vessel, and then the 3 ports on the side, and then the effluent sample. So we were able to do 9 samples, or take 9 samples from each of these locations, and then analyze them for the 16 different PFAS compounds. Our laboratory was using the ISO 25101 method, and we did this weekly starting in February 2018. The data I'm going to present is through December 2019. Our sampling efforts do continue, though most of what we do has been impacted by COVID. So we'll get into the observations. So up front, we'll take a look at the influent PFAS composition. And what you'll see on this plot is essentially just time on your x-axis, and then concentration in parts per trillion on the y-axis here. And what we detected of the 16 that we looked for, we routinely got detections for 5 compounds, and those compounds are highlighted or bolded here on the side. And we did make a designation between the long chain and short chain at 7. I know that's kind of a floating target in the literature, but that is how we made the designation in this research project. So we saw PFOA, and what you see is really PFOA was the major contaminant here. We did have consistent detects for HPA, PEA, HXA, and few for PFAS, but really the driver as far as the design for this system was the PFOA concentration. I was a little curious, or we were a little curious, when you take a look at the shape of this curve, the kind of the questioning why it is that we would have somewhat of a fluctuation in the concentrations with time. We were able to take the monthly operations report from the system and take a look at what the demands, or not the demands, but what the processed water was. And when you overlay that, so that would be this plot here, when you overlay that with the concentration, there's pretty good agreement between increased usage, increased pumping, and an increased concentration. And this makes sense in this particular case because the contamination is from an industrial installation, which is upstream. The wells are down in a valley. The industrial application is up on a hill. And so as they're increasing their pumping, it looks that the Kona depression is increasing, or the Kona influence is increasing, and they're getting more of that PFAS mixture. So I didn't put together a plot of PFAS at the effluent because there were no detects. At no time during the observations or the sampling that we did we find any PFAS compounds in the effluent water leaving the contactors that was then being chlorinated and sent to a clear well and sent to distribution. So we never saw any detects, so that's why I did not put together that plot. Instead, what this plot represents results from the midpoint, which should be here. So at this point, when we started taking our samples, vessel 1 was the lead vessel, and vessel 2 was the lag vessel. So 2 vessels in series. So what we saw, and some of these plots are going to get a little bit noisy, but if you could focus on this first section here as we go through these contaminants, you'll see we detected PFBA at the midpoint of this system, also PFPEA and PFHXA. We did have a single sample that came out, PFOA, at the midfluent, but that was later discredited as a laboratory anomaly. And the same thing could be said for a single PFBS that we saw, as well as PFOS, this sample here, and PFNA. We had one sampling event where all of those compounds came out. It looked to be, when the lab looked at their QA/QC, that looked to be an artifact of lab contamination. So that was not a real result. So what we do see is that PFBA made it through the first vessel, as did PFPEA and PFHXA. What you see here is the changeout. So at this dotted line here, this was the first changeout where vessel 1 received fresh carbon, virgin carbon, and vessel 2 became the lead vessel. So now vessel 2 was the lead and vessel 1 was the lag in the system. And what we observed, or what you could observe, is this lag, the 70-day lag between the changeout and when we started to see PFBA again at the 25% mark of, or at the midfluent, my apologies, at the midfluent of the system. And again, this line here represents another change, and there was a lag after that change of 180 days until we got detection at the midfluent again. We'll go back to these two, because initially it's, when you first look at it, it's curious. Why would I have 70 days before breakthrough at the first change and then 180 days? There's not much changing in this system. The demand rates are fairly constant, so it doesn't make sense when you first look at it, but we'll revisit that after we see some additional data. So from the midfluent, what we did was we took a look at where PFOA was. And again, to kind of borrow from Susan's presentation, where she was describing the greater the bed depth, it seemed the more effective the treatment. That's really what we're looking for when we're doing this experiment. We're trying, or not this experiment, but we're doing this research. We're trying to get a sense for what the mass transfer zone looks like. How deep is the mass transfer zone in these systems? Because that is really going to be the, that's going to be the driver for the design. The contact time in the tank is going to be, or the contactor is going to be the driver for the system design. So what we saw with PFOA, and again, I would focus first on the data on the left side of this line. When we first started taking samples, we saw that the top 25% of V1 was already at equilibrium. So it was already exhausted with respect to PFOA. So that represented 14 months of operation at approximately 260,000 gallons per day. And you got exhaustion of the top 25%. These vessels hold 40,000 pounds of carbon. So you can make an argument that the top 10,000 pounds of carbon was exhausted in that 14-month period. Going down the contactor, you see that the results at the 50% of vessel 1 here, there's active transport or transfer going on. The concentration is not at the background, which would be around between 500 and 600 ppt, but it's down to 300 ppt, 200 and 300 ppt, and we also see small detects at the 75 point, but we do not see anything at the midpoint. So the active transfer zone looks to span a little over 25% of the contactor. So when we do our change out, so again, to the right side of this line, V2 is going to become our lead. So that's why all of a sudden V2, we start to see PFOA at the top 25%, because that's now the influent. That's the influent concentration. We can see that concentration dropping down to somewhere between 100 and 300 parts because we have active transfer going on in that zone. And a small amount of transfer you can see happening at the next 25% zone. But that's it. And again, we had a change out here in late January of 2019. And so after that change, you can see V1 becomes the lead again, and that's why you're going to see PFOA in the upper portion, if that's our active transfer zone. So the observations from that were that the system is effective at removing PFOA. Unused carbon at V1 after approximately 17 months of operation. So vessel 1, that first 40,000 pounds wasn't fully exhausted with respect to PFOA after 17 months of operation. Only about 13,000 bed volumes though, which isn't a lot. The system was designed for 1 MGD. They're doing about a quarter of that. What is interesting though is that when you take a look at the numbers, the approximate carbon usage rate that you back out of that is just under 1/10 of a pound per 1,000 gallons treated, which is very close, actually agrees with the engineering projection that we got. The engineers had submitted a water quality to the manufacturer. Manufacturer did isotherm study on that data, and they came back with a carbon usage rate of 1/10 of a pound per 1,000 gallons treated. So what that translates into would be, if that system were to keep operating, that'd be exhaustion of 40,000 pounds at 4.5 years of operation. And again, this would be specific for this system, this cocktail of compounds. We weren't really ever or fully resolve the breakthrough curve for PFOA because we never saw that. It never exhausted. We never observed the exhaustion of a full zone. So I know I said that we had other short chains, but the other short chains that we have, I decided just to show PFBA here because it was the shortest of the short chains that came through. So essentially the information that we have here is just bracketing the chain length of the PFAS that we observed. So this is going to be a little bit more hairy to present, but there were a couple ways I wanted to try to make this work, so I'm gonna go with one or maybe both of them. So again, the same setup here. On the x-axis, you just have time of observation. On the y-axis, you have your concentration of PFBA in parts per trillion. So again, when we initially, and this is the plot that we saw before, the midpoint, we saw that when we first started taking samples in February of 2017, PFBA had made it through the first 40,000 pounds of V1, and we were detecting it at the midpoint. At the top 25%, we had low-level detects of PFBA, meaning that system that part of the system was exhausted with respect to PFBA uptake, which is consistent with us seeing it at the midpoint. We would be making the assumption that if we're seeing it at the midpoint, we should see exhaustion through each of the sampling ports in V1. And that's what we saw. So V1 at 50, we saw low levels of PFBA, and then at 75 as well. What's different here is that we were also seeing it not only at the midpoint, but it was also being found at the top 25% of V2, as well as the top 50% of V2. That's what we observed before the first change out in May of 2018. So not only had PFBA made it through the first 40,000, but arguably PFBA had made it through the first 60,000 pounds of carbon in the time that it took PFOA to just get down into the 50% zone. And again, it's consistent with what the literature presents on the relative affinity of PFBA to PFOA. And I think to go back to this plot here, I know earlier we took a look at this and I had a 70-day designation between that first change out and the first detection of PFBA here. Let's see if I can get this cursor going again. And then 180 days here, and it turns out what that's probably a function of is that when we made this change, PFBA had made it through 75% of V2. So really this represents, that breakthrough represents only about 10,000 pounds of carbon before we saw that. When we got to our next change here, it stretched out to 180 days because we had more virgin, quote unquote, virgin carbon with respect to PFBA. And in the interest of time, I'll just show these plots. One other interesting observation that we had on PFBA, which is supported in the literature, is that we see this almost a bell-shaped curve that propagates through the reactors. So the concentration, and again, keep in mind that the background influent concentration of PFBA was essentially non-detect. Every once in a while, we would get something above 5 ppt, which was the method reporting limit. So we can make an assumption that the background concentration is floating somewhere around 5, but what we're seeing is that before we would get a detect in the next zone, the next 25% zone, we would see this spike in the concentration, or this peak in the concentration, which we were expecting to see at the effluent, but it was kind of surprising to see this behavior through each of the quadrants of the contactor. And I was just going to present these as separate. I can do that, but you can see, as you know, it's kind of easier to see it presented like this, that concentration, that wave front kind of propagating through the contactor. And so the observations, to distill the observations down for PFBA relative to PFOA, we saw detects through approximately 70,000 pounds of carbon after 17 months of operation. The lead lag design was necessary to maintain PFBA at non-detection at the system effluent. That has interesting design implications because historically a lead lag system is not put in place to provide redundancy. The lag vessel is not supposed to be there for redundancy, but rather to be there so that you can take full advantage of the available sorption sites in your lead vessel. Just in crunching some numbers, 17 months represents, again, approximately 13,000 bed volumes for this system. And when you look at the, when you crunch down the approximate carbon usage rate, it's 5 times what it was for PFOA at about half a pound per 1,000 gallons treated. So to go through 40,000 pounds of carbon, you're talking about approximately 300 days. And again, these results are based on the contaminant cocktail for this specific system, the empty bed contact time for this specific system. And again, one of the interesting observations that we saw was this bell curve type breakthrough, which propagated through each zone. That's something that may be related to the loading rate and is something that we would be interested in taking a deeper look at. Final observation, we do see competitive sorption, or we do see that the longer chain PFOA compounds are making their way through the contactor and are driving off some of the PFBA that has already been taken up by the contactor, and that would be the reason, or the mechanism behind why we're seeing increases in the PFBA concentration with time. It's certainly not that the reactor's creating PFBA. There's no background contamination of PFBA in the reactor, but what looks to be happening is that the PFBA that is parked at an uptake site, because PFBA is going to rush out well ahead of the PFOA, those parked PFBA molecules are later being displaced by PFOA as it makes its way through the contactor. And just quickly, the conclusions supported what we understood from the literature. This particular system was a robust design for PFOA. When you're looking at the design, or you're looking to design, or you're looking to review a design for PFAS with GAC, you're going to want to be mindful of the co-contaminants that are in that system as well, and what the treatment goals are for that particular system. And and another thing that we were interested in seeing with this system, a GWIDI system that has a pretty extensive pre-treatment, you'd have to look at these results relative to that. So in a sense, you could almost say that this system, or the performance of this GAC contactor, would be a best case scenario. I mean, maybe best case scenario is overstating it, but to look at this system and look at this performance relative to what you could anticipate for performance from a surface water system that may have a much higher organic loading, even after some pre-treatment, the organic loading onto the contactors will be higher than what we're seeing in this system. So that's something else that would have to be considered. And with that, I'm over my time. So I'd just like to, again, thank EPA for this opportunity. I've had an opportunity to attend this workshop, and I do think it's a fantastic workshop. So I'm very pleased to have been invited to provide this talk. I would be remiss without mentioning Courtney Davis, who really did a lot of the heavy lifting, putting the presentation together, coordinating the sampling. Along with Cameron down Savigny, he did a lot of our data crunching. And with that, I will turn it over to Tom. Thank you.
Okay, great. Thanks, Scott. Thanks for the great presentation, and thanks to all our presenters. And so this is the time where we will try to share our webcams. So David's up already, so I don't know if Scott and Susan can pop up. Great. And so this is for the next half hour or 25 minutes. We have got plenty of time. We're going to use it as an Ask the Experts type of situation. So we've got a bunch of questions from the presentation, so we'll go through those. Also, if you have other questions that have come to mind during the question period, feel free to put it into your question little dialog box, and we'll try to get to them over the next 25 minutes or so. And frankly, if you have other questions about PFAS that are just burning inside you, feel free, and we'll find somebody that can answer that. So I'm going to start. I'm going to give Scott a little break because he just finished talking. But I'll start with a few questions for Susan, then go to David, and then move down to Scott. But again, if you have any more questions, just put them in, and we'll try to get to them all, as many as we can. So the first question, Susan, it is, what basis did you select the 25 sites for the sampling study? Was it related to their size or type of treatment technology, or whether or not they were surface or groundwater?
We tried to, within 25, get as much diversity as we could. So we went for different sizes. We wanted to look at different regions of the country, look at different treatments. So, and basically for a good year, anytime I gave a presentation to people, a drinking water crowd, I asked for volunteers. Some of those people volunteered. I did the cold calls to allow locations. But basically, we just tried to emulate what was going on in the U.S. in a very, very small sample size of only 25.
Okay, got to unmute myself. All right, here's another one, Susan. So you discussed on certain slides number of PFAS detected. How many were being measured? How many were being measured within that method?
I think we were looking for 17. It's been a while now, but I tried to make the slide panel to be close to the number of compounds that we're looking for, just so you can kind of see that it was a pretty large percentage of what we're looking for that we found.
Great. And one more, and then I'll move on to David. So how was the method of sampling at certain depths were done? And so how did you determine that? And did you consider that surface sampling might pick up more PFAS?
The USGS folks, the field crew, were really pretty instrumental in determining the depth. So I'm not quite sure of all the data that went in behind that. It was just more to make sure we were getting we had discussed, do we want to do depth and with integrated sampling, and that just seemed to be a lot more trouble. So we just kind of decided getting below the surface would give kind of a better idea of what was well mixed within the system.
Okay, great. Okay, David, there was, for those places was there any training or for sampling techniques with regard to those entities that collected their own samples?
Yeah, that's an excellent question. We did work closely with contractor and with Eurofins that was doing the analysis to come up with something that was easy to follow, just a couple pages for those entities to follow on just kind of proper sampling technique and collection. So we did provide guidance, and I'd be happy to share that with other states that are interested.
Okay, great. So for the fire districts, what was the mechanism of contamination at the fire district?
The mechanism of contamination is most likely from just having the PFAS foams and that on the truck. So they were testing their own water wells. So these weren't samples collected at actual sites where they use the foams on fires, but at their own fire stations. And so, talking with a couple of the fire stations that did test high, it's probably just from washing off their trucks and stuff like that. And when you're looking at like a parts per trillion level, you're really looking at, I remember, we try to explain this to the general public of it's a drop of detergent in miles of railway cars stacked together. So, I mean, just a little bit like that of washing off trucks and things can really cause kind of a lot of contamination at that level to show up. And so, some of these fire districts were saying they haven't even used the foam in years, that it's expensive to purchase. So they don't even think they had maybe more than, a container or so of this stuff. And then just not knowing the hazards with it, it didn't take much for it to get into the ground and then to kind of cause a site of concern. So, yeah, what's interesting too, I think, to mention with PFAS results, we've seen results where they've actually been using some of the foams to put out fires. And a lot of the newer foams that contain PFAS don't have PFOA and PFAS in them. So you'll get a sample result back and people seem thrilled because it's, look, we don't have any of those, the PFAS of concern showing up, but it also comes back, kind of smoking hot for PFH excess and some of these other PFAS. And so that's something else to, I think states and we're kind of grappling with, is there's so much of this stuff that, there's thousands of these compounds and kind of what do we make with all of this information with that. So yeah, thank you. That's a good question.
Okay, great. And I noticed they put the title slide back up. So if you wanted to see our faces a little bit more, you can drag down the bar up on the top and make our faces bigger. But I have to warn you, I have a face for radio, so do that at your own.
What about smaller? Can they make them smaller?
Indeed, they can. And that might be the best thing. But okay, here's another one for you, David. For the states who are in the process of developing their own state action plans, what are some of your lessons learned from your work, and what are the most important pathways or sources that other states should address?
That's a really good question. With our action plan, I was contacted by another state. They were looking at hiring a contractor to help them put one together. We did this internally with just our own kind of team and department. And I think a big thing is deciding on even just the terminology. So how are you going to explain? Are you going to call it PFAS? Are you going to call it toxic foam? Are you going to call it, what term are forever chemicals? So there's lots of, even just agreeing on terminology can be a hurdle. And I think one of the things that's kind of difficult is things are moving so fast with information that we're getting of, possible exposure pathways and all of this information on health effects, in that it's so rapidly developing that, you've almost kind of got to have a mechanism to, once you put a plan into place, I think, to be kind of nimble with it and to be able to adjust as you're getting new information. And one thing that we're working on, this has come up just because we've done a lot of stakeholder work statewide, and people want to see, other than having a plan, you've got to be showing how you're making progress and what you're doing with that plan. And so one thing we're trying to do is to get a lot of our PFAS information that we're collecting and then finding a way to make it easily digestible to the public and getting it out there to show how we're making progress on our plan. So that's one thing that we're trying to work on. But those are all considerations to think about when you're putting one together. And I think trying to keep it simple with a few targeted goals will help. Just knowing what you can try to work on and what's kind of beyond. You can't tackle too much, I guess, is what I'm trying to say. So, yeah, hopefully that's helpful for you.
Gotcha. And kind of a follow-on question to that, should other states be concentrating on PFAS in drinking water or other pathways? Or should they concentrate on other pathways?
I don't know. That's a good question. I think that's something that, as a state, you've kind of got to know kind of who's being exposed and how are they being exposed. And for us as a state, you know, there were huge concerns with drinking water just from testing and levels we were seeing. And so as a first step, it was, what are the levels in drinking water? And so we had to kind of grapple with that as a first step. And now, you know, it's, you know, we did only test half the system. So did we even test the right half that signed up, or what, you know, what are the levels in the other half? So that's our main exposure pathway that we're addressing, but we're keeping an eye on states that they're doing a lot of work in biosolids and other things, and, you know, what's showing up in foods. And, you know, if there's something that jumps out, then we'll have to, you know, kind of also start addressing that, or maybe shift priorities. Tom, you're muted.
Thanks, David. I need all the help I can get. Scott, I hope you had a chance to catch your breath. For your system, how was the spent GAC handled?
So the spent GAC for this system, this specific system that the specific manufacturer has that undercone design so that it makes it easier to flush out the carbon. That carbon was then taken to a reprocessing facility. So it was going to be recycled, or at least the potential for it to be recycled was going to be reserved. The health department is still, I don't know that we've finalized a policy on the use of recycled carbon. So I know certainly at the time of the change outs we had not, but this facility was sending that carbon to be regenerated, and then it was going to be stored pending pending a policy decision.
Okay, great. All right, so here's another one for Scott. So did you, in your columns, the lead lag columns, did you ever have to backwash the GAC due to head loss?
You broke up a little.
Was there an issue?
You broke up a little bit. Question, but I think what I heard was, were there any backwashes that were conducted while we were sampling?
Right, yeah. What did you do with backwash? Was there anything with the backwash water that you did in particular, and do you think that affected the breakthrough profiles, if you did it?
So to my knowledge, there were no backwashes between change out. So obviously when there's a change out, the new carbon is put in, it's fluffed up with a backwash. That's being backwashed with treated water though, so there was no PFAS contamination in that water. So that backwashed water was just being sent to waste. I don't believe there were any backwashes after carbon change out, and I really think that that's a function of there wasn't an extended period of time with respect to carbon contactors. You try to minimize the backwashes that you're going to use with carbon contactors anyway, because you don't want to be affecting the shape of the carbon. So usually if you can go a year, that's kind of your gold standard. You're going to go for a year before you have to do a backwash. There were no head loss issues that would have triggered a backwash for this system. So to my knowledge, there were none between change outs.
Okay. You presented all the breakthrough profiles. Did you have any, are you moving toward, or do you have any interest in modeling the breakthrough profiles with absorption models to see if you might be able to apply it to other situations or other utilities?
Yeah. Sure. I guess the answer to that is I'm very interested in that, but I think my interest in that outpaces my expertise in that. I know we have in-house expertise that has approached this research group and asked the same question. You know, we have enough data. Can we now start looking at applying models? So we certainly have the data to do that. I'm interested in doing that, but we have not moved to that yet. And we would have to, as with anything else, we'd have to balance that with the various priorities that we're working on.
Okay, great. Oh, just as an aside, if you need EPA software, we can help you with that.
Okay.
Last question for Scott, and this is along the lines of what we asked David. What's the best way of dealing with PFAS within your state? How do you best communicate it in terms of if there's PFAS in communities' water? You know, what concentrations are they at, and kind of how do you best take your lessons learned and apply it to other utilities?
Yeah, that's a big question. It's kind of outside of my shop. We do have an outreach and education group that I don't want to say struggles with that, but it's a very difficult thing to do. It's a very difficult thing to communicate the tox impacts for these compounds. It's a very difficult thing to discuss treatment targets or treatment goals. So my camp is more focused on what's the number, how do we get there, and we do have other groups at the health department that are focusing on and working with the tox folks to make communication effective. If they had me doing it, it wouldn't be what it needs to be. So, but we do have a group that is trying to, and I think like David said, there's a lot of pressure on what your initial product is going to be for that, because it becomes difficult to step back from something that you've said. So there's a lot of time and effort that goes into figuring out what the appropriate way to communicate that would be. So I don't know if that's the answer that they were looking for, but that's what we're trying to do at the state of New York.
One thing too, I think that's worth adding in just on that question, I think just makes it difficult, is we've got a utility that has granular activated carbon installed, and partly what they're wondering is, you know, is this large plume coming off of a PFAS source that's not too far away? Is that moving towards us in the ground, and at what levels could we see? And so they have treatment right now, but they're worried about, could there be a doomsday scenario where all of a sudden this plume hits them at levels that they can no longer treat for with the granular activated carbon, and then to throw in just kind of regulations in general, you know, what's going to happen, you know, for PFAS, PFOA, the MCL that'll be set nationally, what are states going to be doing and regulating other PFAS? And, you know, Scott was highlighting PFBA and some of these shorter chains that kind of rip through carbon in some of these treatments a lot quicker. And so it makes designing now, I think, you know, there's a lot to it, wondering, you'd hate to put something in now that works to find out, you know, later down the road, the game's changed. Based on what you're seeing in your influence or other PFAS of concern. So those are just other considerations, I think, you know, for states and others to be aware of.
Yeah, I think that it kind of goes toward what Susan, some of your data shows on the variability of PFAS in water. So Susan, how you know, do you feel that this variability, is it due to just changing sources? Is it due to complex mechanisms happening within the system? You know, and is there an opportunity to do a better site characterization, if you will, of a certain watershed or groundwater to help out utilities so that they might know what is coming in the future?
Yeah, I mean, definitely we saw a range, not only for the PFAS compounds, but for the other CECs we looked at. The ones that are wastewater derived, they tend, especially if they're well linked to the wastewater treatment plant, if they're close in proximity, you might have increases. Just the hydrograph coming out of the wastewater treatment plant fluctuates during the day based on the morning flush coming through, that type of thing. But for PFAS in particular, yes, I think there's a lot that we need to do there. And I've been working on a book chapter looking at some a review type book chapter, and concentrations in groundwater tended to be higher for PFAS compounds than it did in surface waters. So that was, kind of surprising to look at when you saw the data together. So definitely, I think, groundwater might be something more important to look at than we have been for the other CECs.
Right. Okay, so do you think that this variable influences, and do you think that, so we had questions about why would the effluent concentration be higher than the influent? Is it with regard to variable source water concentrations, or is there something else in that regard?
I think the questions are directed to me on my study. We'd asked the utilities to try to pair their source water coming in and their treated drinking water coming out. So we're looking at the same parcel, but they may have not done that as well. Additionally, there is some work looking at precursors that might be forming the PFAS compounds during treatment. I think maybe more on the wastewater side than the drinking water side, but still it's possible. But we did not monitor for any of those precursors, so we can't say one way or the other if there was conversion or production being done during treatment. So, we're really not sure why exactly in some cases the effluent was higher than the influent in our locations.
Okay, good. Yeah. Oops. Am I muted? I might be. Nope, I am not. That's good to know. Okay. And finally, Susan, what kind of matrix interfaces? Because that's an issue too in terms of waters at various different types of ambient waters. You run into matrix interference problems. Did you run into any of those in your study?
Yeah, unfortunately, it looks like my screen cam really kind of froze at a unattractive place, but sorry about that. But yeah, so I didn't mention it, but in our study, we really did a lot of QA/QC on the samples. We collected every sample in triplicate. We analyzed the primary sample, a duplicate, and then a matrix spike. And then we flagged samples that had recoveries greater than 150% recovery, just because, at that point, we really couldn't be sure of what concentrations we're dealing with, just because of matrix enhancement. On the flip side, if we had these matrix spikes showing very low recovery, there are some samples that we are only getting like 50% recovery, both on the matrix samples and the laboratory spikes. If it was doing that, we did not report the data for the samples. So definitely QA/QC was a big part of what we did. And I don't think I answered the question exactly. I got caught up on the details, but yeah, definitely, incorporating a lot of QA/QC, not necessarily as much as we did, that study had 75% QA/QC going on, but doing a few samples here and there. That review study I was mentioning, it was just kind of disappointing how few QA/QC is reported in the literature. I was kind of writing it down and just, enumerating it in that way. It was really eye-opening to me how little is being reported. And if you're doing it, you might as well report it, just that way people can be sure in the data you're seeing. So that's my soapbox for the day.
Okay. Question for Scott as we kind of wrap up. So what triggered the carbon change out? Was it PFOA at the midpoint or PFBA at breakthrough? And along with that, what do you think the competing absorption or the co-contaminants that were competitors for absorption sites, what do you think they were in the case of your project?
So on the first point, or the first question, really the answer was neither. We happen to see PFBA where it was, but I think what triggered the change was contractually or the design had a change set in at a certain period of time. And I don't know if it was, we had that change at the 17-month mark. So it was really a maintenance driver. And I know it sounds weird to say a maintenance driver when I also said there was no pressure drop, because there wasn't. But the decision was made kind of more as a maintenance. The design was for a change out of 12 to 14 months or a little bit behind that. We happened to see the compounds where they were, so I think it just made sense to do it. But it wasn't that PFBA was the trigger for the change. And the second part, the co-contaminants with desorption, I'm not sure I follow exactly the question. The point I was trying to make with the, oh, sorry.
Yeah, you mentioned at one point that PFOA was chromatographically pushing the PFBA ahead. Do you think there were other things other than PFOA in the water that was doing that too?
That I don't know. I mean, certainly I think you can make an argument that any of the compounds that had a longer chain length than PFBA have the potential to do that. And that is something that I would really like to dive into the data, because like I said, I can't rectify in my own mind that propagation wave. I would understand that at the effluent, because I could see that you were getting PFBA driven in the upper portion of the contactor. But if that PFBA is coming off the contactor in the upper regions, and we've already established that the lower regions are exhausted with PFBA, I don't know what's slowing that up. And so that's something that I would like to take a deeper look at. And I'm wondering if it has something to do with the relatively low loading rates that we have for this particular system.
Okay, great. Yeah, makes sense. All right, so we're kind of a little past time, but I'd like to ask just one kind of wrap-up question for each of you. So, you know, what kind of, very quickly, because we're kind of running out of time, but Susan, I'll ask pretty much the same thing to everybody. What area of work for PFAS do you find the most intriguing or the most needed right now to help communities and states? What aspect is of interest to you right now or concern?
Well, not just with PFAS, but for all CECs. Right now, I'm really concerned about, or want to look more into household wells, especially those that are close to septic systems, because I think there could be hotspots there for CECs that we might be missing. Large river system, I think we got the dilution going, so it helps, but the households where, you know, might be really linked between the septic and the home, that's where I want to look more.
Okay, so David, what's the most concern in Colorado or of interest to you with regard to this topic?
I think right now with PFAS, the biggest concern is just finding out where do we have just kind of a PFAS hotspot map. So who's using the chemicals and where could there possibly be contamination in the ground or in surface waters, and then figure out who could be exposed to that. You know, private wells are a huge concern. We've seen it show up pretty high in those, and then making sure that along with that, there's not any public water systems pulling water out of those areas.
Okay, and Scott?
Yeah, so for me personally, I'm a treatment geek, so I'm interested in the treatability and the treatability of the, you know, not just PFOA and PFAS, but of the mixture and the shorter chains. I think a broader interest, the state, just like David is saying, I'm interested to see where we find it. We did promulgate an MCL for PFOA and PFAS. I think it went into our state register last week. So that's going to start the clock on monitoring. So we're kind of at the precipice of answering that question in New York State as the results start to come in. Where are we going to find it?
Okay, great. Well, thank you so much, Susan, David, and Scott. Great presentation. Thank you to the audience for hanging in there. We had great attendance today, and I apologize for any quirky video or audio problems that we had. You know, it's the ghost is in the machine kind of thing. Who knows how these things pop up, but I hope it didn't impact you too much. Again, these presentations will be made available, and so will the recordings of them. So you can always go back and look at it that way. So this concludes this session, and we're going to reconvene at 3:30 Eastern Time in about an hour for 2 more sessions, one on pathogens and disinfection and one on source water quality and protection. So that will kick in at 3:30 Eastern Time. So the people on the West Coast and can have lunch, and the people in Hawaii can have some brunch or whatnot. So the things we have to deal with when we do a virtual workshop. So thank you so much for everybody attending, and thank you again to our speakers who did an outstanding job. And hope to see you at 3:30.
Thank you, Tom.
Thank you.